Hey everyone, and welcome to this explainer. Have you ever just looked around and realized that the entire world is kind of built on hidden mathematical patterns? Seriously, from the spirals on a pine cone to the way your money grows in a savings account, math absolutely isn't just some random collection of numbers locked away in a heavy, boring textbook. It's actually the invisible code of our everyday lives. So today, we're going to decode one of the most elegant, fundamental patterns out there, arithmetic progressions. We're going to uncover the hidden rules behind these sequences, and honestly, we'll learn how to completely master them. Let's get started.
But before we dive into all the formal definitions and formulas, I really want to present you with a bit of a mystery. Just picture this. Imagine a schoolhouse back in the late 1700s. The teacher wants to keep his students quietly busy for a good long while, right? So he gives them this seemingly brutal, mind-numbing task. Add up every single whole number from 1 to 100. Yep, 1 plus 2 plus 3, all the way up to 100. By all accounts, this should have taken hours. And yet, there was this 10-year-old kid named Carl Friedrich Gauss, who literally wrote down the answer almost instantly. No calculators, no smartphones. How on earth did he pull that off?
The exact number he scribbled on his slate was 50-50. Now, I know it seems completely impossible to crunch that many numbers in your head that quickly, but here's the secret. Gauss didn't do it by brute force. He didn't just add them one by one. He took a step back, and he saw a pattern, and I promise you, by the end of this explainer, you're going to understand the exact mechanics of that pattern. You'll know precisely how to pull off this brilliant mental trick yourself.
Okay, let's dive into this. Here is our roadmap to demystifying all of this today. We'll start with Section 1, Patterns in Everyday Life. Then, Section 2, Defining Arithmetic Progressions. Section 3, Finding the nth term. Section 4, The Genius of Gauss. And lastly, Section 5, Summing it all up.
All right, moving right into Section 1, Patterns in Everyday Life, Math in the Real World. It is so absolutely crucial to realize that the math we're exploring today isn't just some abstract theory. It's super practical, and it's happening all around us. Let's look at a really grounded example.
So, think about the story of Rena. She applies for a new job, nails the interview, and gets hired. Nice. She's offered a starting salary of 8,000 rupees a month, plus an annual increment, a guaranteed raise, of exactly 500 rupees every single year. Now, if you track her salary from year 1 to year 4, you spot a really relatable pattern. It goes 8,000, then 8,500, then 9,000, then 9,500. We definitely don't need fancy math vocabulary to see what's going on here, right? Every step forward is just a simple, predictable addition of exactly 500. And let's look at another super tangible example. Meet Shakila. On her daughter's very first birthday, she drops 100 rupees into a piggy bank. Then, for every birthday after that, she increases her deposit by exactly 50 rupees. So birthday 1 is 100, birthday 2 is 150, birthday 3 is 200. You get the idea. Just like Rena's salary, we're looking at a fixed starting point and a fixed, unchanging amount that gets added every single step of the way. Okay, so we've seen these patterns play out in salaries and piggy banks. Let's shift gears now to Section 2. Defining arithmetic progressions, translating to math. This is where we get to our core definition. An arithmetic progression, or an AP for short, is really just a list of numbers where each term is found by adding a fixed number to the one right before it. To make this super easy to work with, mathematicians use two main characters. First, we have the letter A. That just represents the very first term in our list. So for Shakila's piggy bank, A would be 100. Then we have D, which stands for the common difference. That's the fixed number we keep adding over and over. For Shakila, D is 50. See? Simple enough. Now, it's worth pointing out that not all progressions are exactly the same length. You have a finite AP, which means it actually stops. It has a definite last term. Think of the rungs on a ladder that get 2 centimeters shorter as you climb, starting at 45 centimeters and ending exactly at 31. That sequence has an end. On the flip side, consider the infinite AP. This one goes on forever, literally, like our basic counting numbers 1, 2, 3, 4, and so on into infinity. And actually, knowing whether your list has a last term or not is going to be super important when we try to add them all up later. Which perfectly tees up Section 3, Finding the nth term, time-traveling math.
We know how to step forward one term at a time, but what if we want to jump way ahead? Like, what if Rena wants to know her exact salary in her 20th year? We don't want to painstakingly write out 20 steps. Look at how an AP is built. The first term is just A. The second term is A plus 1D. The third term is A plus 2 Ds. The fourth term, a plus 3 d's. Do you spot the hidden rule? The number of d's you add is always exactly one less than the position of the term you want. Want the fourth term? Just add 3 d's.
And that observation? That's our mathematical master key. It gives us the nth term formula. Check this out. A sub n, meaning the term we're trying to find, equals our starting point a plus n minus 1 multiplied by d. All we do is take the position we want, subtract 1, multiply that by our common difference, and add it back to our starting number. Boom. With that single line of algebra, you can basically time travel to calculate the 100th, the 1000th, or even the millionth term of any arithmetic progression.
Armed with that incredibly powerful tool, let's jump into Section 4, the genius of Gauss, outsmarting the teacher. Let's go back to that opening mystery with our 10-year-old math prodigy and figure out how he pulled off his stunt.
Remember, Gauss was tasked with finding the total sum, which we'll call S, of the numbers 1 through 100. S equals 1 plus 2 plus 3, all the way up to 100. Now, instead of just plodding along and adding them from left to right, Gauss did something next level. He imagined the exact same sequence written in reverse, right underneath the first one. So, the reversed sequence is S equals 100 plus 99 down to 1. He essentially perfectly stacked the smallest numbers right on top of the largest numbers.
And here is where the magic happens. Step 1. He added the two equations together vertically. S plus S gives you 2S. Step 2. He looked at those vertical pairs. 1 plus 100, 101. 2 plus 99, 101. 3 plus 98, you guessed it, 101. Every single pair adds up to that exact same number. Step 3. Since there are 100 terms in the sequence, he just multiplied 101 by 100, which gives 10,100. But wait, step 4. That's the sum of two sequences combined, right? So to find the actual sum of just one sequence, he just divided that 10,100 in half. And there it is, 50-50. He literally transformed a massive headache of addition into one simple multiplication problem.
Honestly, that is such a brilliant mental leap. But the best part is, we don't need to be 18th century child prodigies to use it. Moving into Section 5, summing it all up, the universal formula.
We're going to take Gauss's specific trick and turn it into a universal formula. Take a look at the general sum formula. I know, at first glance, it looks a little intimidating with all the brackets and letters, but let's break it down. S equals n divided by 2 multiplied by 2a plus n minus 1 times d. This is literally just the formalized algebra version of Gauss pairing up numbers. The n over 2 part, that's just taking the total number of terms and cutting them in half, because we're making pairs. The rest of the formula inside the brackets is just figuring out what that paired up total will be, based purely on our starting point and common difference.
But hold on, it gets even better. There's a cheat code here. So we have the standard formula we just looked at, which is great when you know your common difference, d. But then we have the shortcut sum formula, S equals n over 2 times a plus L. Here, L simply stands for the last term. If you're working with a finite arithmetic progression and you already happen to know the very last number in your sequence, you don't even need d. You just add the first term and the last term and multiply by half the number of terms. Talk about a massive time saver. So let's bring it all together. Let's consolidate everything we've uncovered into 3 really powerful takeaways. Number 1. The general form of any AP is just a starting point A and adding a common difference D over and over again. Number 2, you can jump forward to find literally any specific term using the formula AN equals A plus N minus 1 times D. And number 3, you can sum up the whole sequence in seconds, just like Gauss, using S equals N over 2 times the first term plus the last term. We've gone all the way from everyday piggy banks straight to incredibly powerful abstract algebra.
And that leaves us with one final, kind of mind-blowing thought. Math isn't just about passing a test. It's a lens for seeing the world with total clarity. If the predictable patterns of our finances, of nature, and of numbers themselves can be unlocked with nothing more than simple, structured addition, what invisible mathematical sequence are you going to spot next in your own life? Seriously, keep your eyes open, because the patterns are everywhere. Thanks so much for joining me on this explainer, and keep exploring.